I know I'm hard to manage in talks. Because I don't keep track of time and there's no clock.
So shall we get started? Yes.
The video is recording.
Okay, so for the first session of this, first of this morning session, we have Eveliina Peltola will give the last lecture on the probabilistic tools for CFT.
Thank you. And actually, maybe we'll see some tools today. So we see some tools to see BBC equation. And so I had planned to fill in the board with all kinds of stuff, but then I got lost in the forest and made a 40-minute detour. So I only filled this one. And I don't know if you see, so it's the same formulas we saw yesterday, but I think it was quite quick. And I can elaborate here. So the idea was to look at these SLE type random curves and how they interact. So there's a tiny picture, right? So remember the motivation from lattice model would be that we have some alternating boundary condition, maybe plus and minus in the easing. So I make some color here. And because we are in 2D, we will have interfaces between the plus and minus clusters. So they are yellow here. And they connect somehow. If you have many of them, maybe here this one goes to that point, etc. And those points, I should tell you, they are sitting some disorder operator that maybe I don't know mathematically what it is, but it's generating these curves somehow. So those points I call x1, x2, etc. And they're going to be on the boundary. So we have boundary CFT. And so I told you yesterday how to understand one curve. Remember? You can do it here. So we are having conform invariance, so we could actually be in the half plane. Here I'm drawing a disk because it's easier to draw, right, for the curves. And one curve, if you want to grow, you can do this kind of Liouville evolution. Which is saying that, let's say it's a curve gamma at time t. I can uniformize. So let me assume this kappa parameter is small enough. So there's some numerology here. I'll get to that soon. So here I have the image of the tip. Maybe we make it red. Right? And I want to grow the curve by some conform map that's kind of zipping this. So I would be having a map, which is in my notation is the inverse of this that I call GT. And for each time t, if I know where is this point, and I know this map, right? Then I get this curve. So that's the point. So the GT, which is a map from H minus this segment back to the H, solve some equation. And I can invert it. So this is conformal bijection, normalized in some way. And once I know how to invert it, I know where this tip is going. Once I know this one, right? And now for the one curve, this one is just Brownian motion times some speed. Right? That's what I told you yesterday. So we get random curve. The randomness comes from this Brownian motion. So this is in one dimension, right? Because it lives on the real line. We get a two-dimensional curve from one-dimensional thing by these conformal maps. So this is called Liouville evolution. And I get this random curve, which people call SLE kappa curve. And so how to see some more CFT in the sense of correlation function is that we can study how several of these curves interact. So this picture has more of them, right? And I was trying to tell you yesterday, which was a bit quick in the end, how you cook up the several curve model from the one curve model. So the formula is there, but it's a little bit maybe, if you're not used to measure theory, it's hard to grasp, and I hope it's not too small. But so many curves. What is the idea? So if I have two, maybe now, so this is somehow going to infinity, which is one boundary point. Well, let's move infinity to somewhere, maybe a couple of other points. So now if I want two curves, let's say this one and that one, right? What do I expect? So I would like maybe them to be individually described by this one, but also have some interaction. Maybe this is gamma 1, gamma 2. I think I was calling it eta maybe before, but anyway. So I want to say some symmetry, because again, from this lattice model description, if you have, imagine your Ising model, which is in the boundary domain is easier to understand, the pluses and minuses. In the boundary, if you put plus, minus, right? So you have those. But now if you explore this bit, all the pluses on this side, we go there. And on the other side, there are minuses. It's the domain wall. So if I already know this one, I can somehow forget about it, right? And so what is this one? Is just the one curve, but in the different domain. Yes, I have to remove this one. So now here I have all the way plus boundary. So we have this kind of resampling property that we started to call it. So we postulate this property and then we construct measure that satisfies it, okay? So what does it say is that the conditionally on this one guy, or several if you have, what is the distribution or law of the other one is the SLE kappa distribution, but in, let's see, a half plane minus, I don't know what to call this. We call it A2, which is like the interior of this, right? So I want this kind of property, and it somehow forces me to have a certain type of construction. So what I try to do in this formula is that first we can try to say, okay, let's take them two independently. So I had this symbol there, which is like product. I can have J curves. So now gamma vector is going to be gamma 1, gamma, I don't know, n. So J of them, and I could have, what did I call it? Maybe P SLE. I think I call it 1 SLE, and I put here independent. So it's the downstairs over here. It's a little bit small. So if I just take product measure of independent curves, what does it mean? I just put them independently, but then they don't have this property, right? So I need to put some interaction. So this is somehow wrong. So need interaction for this. And the interaction you need to figure out. And I was telling you about this conformal anomaly. So we had some knowledge about how this curve is responding to change of domain, and exploring this bit is a change of domain. So using that formula, we can come up with this, this one here. So what is here? There is the central charge, which I wrote here. Maybe you like better than 13 minus 6 times theta plus 1 over theta. So it's the C less than 1 region. Coulomb gas or whatever you want. So the central charge is telling you the strength of the conformal anomaly. Then there's this kind of anomaly term that you could write using Laplacian determinants we've seen in talks. You can use Polyakov-Alvarez formula or some other formulas, which actually are not finite for these fractal curves, but heuristically you could do that. So a rigorous way to do it is to write using Brownian loop measure, which I cannot really describe to you, but it's essentially measure on loops of two-dimensional Brownian motion living on this domain. You put kind of a lot of them there, And you see how many of them touch at least two of those curves. So if you only have two curves, it's kind of easiest to understand. So then by inductively, you can do this. So there's some kind of interaction term there, which is exactly what I need to put. So I think it's impossible for you to, if you haven't seen, like to understand really deeply what it is, but I hope it makes some sense. And it's very symmetric, like I don't decide which curve is my favorite, they're all there, right? And they all interact in this homogeneous way. And so then downstairs, I just put normalization constant because I want probability measure. And then I need to show this normalization constant is somehow finite, right? So this would be a partition function. So downstairs is just, what is it in a fancy way is the, for the independent measure, you just average the total mass. So don't worry too much if this formula are not nice. I just wanted to show you that it's concrete. And I want to show you how to get BBC equation related to this. So the point from this conformal anomaly was also that these endpoints of the curves, they matter. So it's not in this formula because I somehow normalized the measure and forgot about it. But you see it in the conformal anomaly formula. Okay, so it's a bit mysterious, but hopefully it becomes more clear soon. And yeah, so from all this construction, we get something that I call partition function. You'd call it correlation function. And it's slightly small. I wrote it last time. So it's essentially wants to have, this one is the same as there, is the normalization factor. But then I need to put the influence of these marked points, which is the prefactor. And the prefactor has, if you're an analyst, you maybe know what Poisson kernel is. If you're not an analyst, you don't probably know. But what is it? It's a two-point function. So maybe I can elaborate this a little bit. So yeah, so somehow you can think about of the interaction to be encoded in this in the partition function. And yeah, so if I'm in my favorite half plane domain, because I said that it's easiest to write formulas there. So I sometimes draw this, but I actually want to work on half plane. So I can write this guy a little bit better. So if I have x1, I need even number of points over there. I think I didn't label them, but I hope it's obvious what the points are by now, right? And by the way, if you want some metric or whatever, you need to keep track of those things, but we are just in the flat. Right, so what is this guy gonna be? It's a product of two-point functions. And I need to tell you the notation. There's some weird indices here. J. Let's see, I think it's 2h minus 2h12. Is it true? Maybe you can protest. I think I wrote it there. I think it's correct. And then this thing with central charge, right? And then this weird loop measure kind of interaction part, which, so what is here, I average over somehow all realizations of those curves, what the interaction is. And this is some prefactor. And so now comes a problem, because if I draw again, let's do a bit bigger, 6 points. And I want those curves to grow from there. Let's say no one is growing to infinity. So there's many ways that they can connect, right? So there's actually many configurations of curves. So maybe I want to fix one for simplicity. And I can call it, keep calling them alpha, so I just use that. So what is it? A pairing of these points, right? So maybe the first pair is A1, B1. You see it in this indexing. Blah, blah, blah. AN, BN. Okay, so this is pairwise 2-point function. So for example, let's say maybe this wanted to go there. So then this is like XA1, XB1, etc. And yeah, somehow maybe it doesn't still tell you why I include this prefactor. But it was in the conformal anomaly formula yesterday, so maybe I don't write it again, but it will be in the notes, okay? So if you kind of think about it, if my signs are correct, this wants to be some CFT object, right? Of some field whose conformal weight is this one. And it's a boundary field. But so I don't know what this field is, but I know what the correlation functions are.
It's the
That's the
product
point.
of those over J.
What's that? Yeah, product J from 1 to n. So for each curve, I take the 2-point function. It's kind of like if you wouldn't have any interaction, just have those 2-point functions. But of course, it's not gonna give this resampling property that I want. So it's, I don't know, it's an overall kind of factor. And then you have this interaction part. So I'm actually still not fully understanding the emergence of this factor, but it comes from these computations. So somehow it's there. And also it shows, so actually I didn't tell you, but the factor, this Brownian loop measure, maybe you remember from Johan's talk. So that's actually conformally invariant. So I can send this domain to the half plane. And what happens to this total mass of those Brownian loops is the same. So there's no anomaly. Somehow the anomaly is already in this central charge. So that guy, this is conformally invariant. But the whole guy is conformally covariant. Because if I send my half plane and the points to some other place, of course this guy, unless this is 0 conformal weight, it's gonna give some contribution, right? It's right covariant. So if I do some Möbius map, is F maybe? So let's say we are in our half plane, so we don't even change the domain, but it fixes the order of the points. So I can look at what is the Z half plane fx1. And because this was invariant, somehow nothing happened. From there, you accumulate something, and what you accumulate is the product of f prime at every point, right? To the power of h1. I think my h12s may have minus signs wrong sometimes, but I hope it's okay. And then times the original one. I think here should be minus. Let me write x vector for the x's, because I'm lazy. Right. So what do you see from here? You see a conformal transformation or word identity of a primary field correlation, right? So I hope it makes some sense for if you're from CFT and you didn't get intimidated by this other thing. So yeah, it's quite a long story to make sense of these objects. But once you do it, you end up with this kind of partition functions, which kind of seem to involve this possibly degenerate field, right? And I was asked to explain why we see BBC equation. Because now, so the H12, it's conformal weight in the catch table. So I wrote it here in terms of the kappa. But of course, you can write in terms of these other parameters that your favorite ones. So we know, so if this field would somehow be constructed, that I don't know mathematically how to do it, but if there's an underlying field, so it seems to be a primary, right? And it seems to have this conform weight H12 in the catch table. So then we know that if it generates some Virasoro module, like it should if we actually have a CFT that's describing all these things. So remember, my point of view of CFT is that I have some observables, which here are these curves, and I want to cook up a CFT that contains that information from those observables. So then I need to figure out which fields should be there. And this kind of field should be there by all this nonsense, right? But yeah, so then the Virasoro module that's related to this, so it can have, so the Verma module, yeah, has non-trivial submodule. But of course, we don't know if this guy generates the Verma module or some quotient. So we need to do something if we want to find out. But potentially, right? We expect a BBC equation at level 2 here. So I'm not going to tell you this story because I'm hoping if you're from CFT, you already know. And if you're not, maybe we can discuss later. So is the picture somehow reasonable? Do you have some question? Need to clarify some bit?
So for a duty, it would be like a conformal block.
Exactly.
And the fact that the Brownian loop measure depends on the connection fixes the internal channel.
Ah, yes. So you see the connection label, and already the prefactor depends on it, right?
Already?
Yes. And then this Brownian loop measure, it actually kind of does because it depends on, it average over those curves which connect in the certain way. So this label alpha, actually you can see how it's kind of a Virasoro label. So it's some kind of conform block indeed, or correlation function. People ask me what conform blocks are. I'm not quite sure. Sometimes I identify them with correlation functions. So if you want to go to the bulk, I'm on the boundary. You can put the points in the bulk inside the half plane, take the complex conjugate points, like in this Cardi trick, if you heard of that. And then you cook up a single valued chi by some combination of these things. So in that sense, they are conform blocks. And the channel is a little bit weird. So you can also try to see, because you may be used to this conform blocks in different channels, right? And the label is kind of telling you that if you do Virasoro fusions. So here, it's not any of those blocks, I think, that's usually in the classical yellow book or whatever, because the Virasoro fusions are something else, which was a surprise to me somehow. So there's change of basis from these to some other blocks in some other channels, and maybe also the favorite ones that you like, which is, well, there's some combinatorial way to do it, or something you can do, which actually wanted to point out, but I think I will not have time to explain. Let me point out here. So, yeah, somehow idea is that this collection are kind of conform blocks. I guess for this kind of phi 1, 2 fields, whatever. And what I want to say, they span some kind of space, maybe complete span. Let me call it some S n. N is the number of points. Okay, so this is a finite dimensional space. Doesn't matter. It's the number of possible pairings. Okay, and yeah, so they are linearly independent. So in particular, so maybe theorem, I should say. I don't know if I want to attribute. It's kind of a collection of various people. So there is Flores and Kleban who worked on this a lot. I worked on it also with Kytälä. I think this was, yeah, in the irrational case. Then I had some paper with, yeah. Anyway, I'll put some reference for you in the notes because I'm very bad to come up with references without preparing them. So there's a lot of works in different kappa values. So somehow the kappa irrational. So maybe we have this minus q. This is easiest somehow. And then the rational ones need some more work. Okay. It's a really long story. But the point I wanted to make that will tell you why these are special is that you can embed, maybe that's another theorem, is that this space embeds linearly to a quantum group module, which I can maybe write in this way. From 1 to 2n now. For each point I put the quantum group module. Okay. I didn't want to give a notation, so it's a two-dimensional module for quantum SL2, type 1. And here I need to say that, yeah, I think actually, especially Azad will be unhappy. Yeah, because, yeah, what is happening in the rational cases.
So in a rational case, you have a kernel. Yes.
What's that?
You have a kernel in a rational case?
We actually think not, because the linear independence, where was it? This is for all kappa, also the rational ones. So somehow this space has the same dimension. What I think is that the kernel that would come here would be kicking out those things which are not in the minimal model. So I kind of mentioned, but didn't really tell you, but this goes outside of minimal model. So I think the minimal models go to the whatever semi-simple part, and then this guy should go to I don't know. Probably you have the Lustig quantum group, etc. So there's some kind of work on this, but I don't think there's complete understanding. I'm really happy to talk about it with experts if you want. But so point.
Do you write this map explicitly?
Yes. It's just that then. Yes, but the problem is that they are linear combination of things with coefficients that blow up and integrals that go to 0. So then you want to say, okay, so 0 divided by time, 0 times infinity is actually something finite. And it's not always so easy to show if you have.
So this is for second line, right? You say when it's rational, this is the work you do. No, in theorem, in first theorem.
Yeah, this is not rational.
No, in the first theorem, previously.
Oh, yeah. So, okay.
This is what you.
Yeah, because we have different constructions, right? Yeah. So the easiest maybe refers to.
Right, so to get this linearly independent in the rational case, you are kicking out the singular vectors. No? You're taking some quotient. Whereas in the non-rational case, there are no singular.
They're all singular. Yeah, that's what I try to tell you soon, that you always have BBC equation for any of these any value. Yeah.
But if kappa is not rational, in the CATS table, you don't have any singular.
You do if
No,
it's in
1,2.
this. Yeah.
1,2, you always have a singular vector.
Yeah, exactly.
For any kappa.
If you have, yeah.
The kappa theta is kappa over 4.
No, for any central charge, right? If C less than 1,
It's the result of taking
thermal module level 1, 2, H12 has a singular vector at level 2 for any central charge.
Not stated as irrational.
Yes. For any central charge, even irrational central charge. And thermal modules are not all reducible for any central charge. Thermal module of the weight HRS has singular vector at level R times S. This is what she's saying.
So I can add also about these singular vectors in the note if you want. I was assuming maybe everyone is familiar with them, but yeah, so we have singular vector actually in any, for rational or irrational.
Mhm.
So somehow, yeah.
It's just for rational, you have more singular vectors. You will have
Yeah,
more
so for
singular vectors.
rational, you could have some, yeah, right,
I just have one.
right.
But in irrational, you'll have just one.
I just have one.
Yeah,
You
it's
just have
kind
one.
of funny because we have some continuity properties in this kappa parameter. I guess I put it even complex if you want. So I wanted some interval, but yeah, so we even know they are real analytic. So I don't know exactly what happens that you approach those. Should investigate what is the regularity of the functions. But in any case, so everything is kind of continuous. So you get a similar picture in any range, but proving it is different sometimes. Or we started from using this Rodchenko-Fatev kind of, so this is like motivated, right, by these integrals that they have. So there you need to find some contours that are appropriate. And there, yeah, you have to assume this because of, otherwise you need to somehow systematically deal with the degeneracies that we didn't want to do. And for the quantum group is also kind of, you know, while then for the kind of full range, you can combine some knowledge from these integrals from the probabilistic construction. So what do I mean by this? Is that formula here, right? So it's maybe not crystal clear to you, but this is completely rigorous and known. But here it's not very clear how to differentiate because you need to exchange derivative and this measure, right? So this one depends on those points. So then there's different difficulties in different methods, and I don't know which one is better, but yeah. So that was a kind of long side remark, is that there's actually a lot of structure underlying here, and a lot of history also. But indeed, I can view this as confa blocks because of this somehow. Yeah. Yeah.
Lina, do we know the correlation function of minimum model inside this SN?
Yes. So I haven't looked everything closely. For the easing model, I did the computation because they are known from, I think, in this paper or yellow book or something. Right? Minimal model correlation functions, they are completely known to my understanding.
I think at least they can somehow algebraically define the
Exactly.
function.
So if we compare with the easing minimal model, let's see. So what I do know is that the energy field, I called it epsilon. So it has, I have the formula written somewhere. I think I put it in the note. So it has some kind of block, 4-point block. What should I call it? Maybe like F. And now if I have 4 points, I can take my favorite ones, right? Maybe one of them is the free variable. So 0, 1, infinity and something. So then it's somehow function of that only for the 4 points. So this is some explicit thing. And algebraic indeed. Formula. And I calculated that, it's the same as the sum of the two things that I have. So now these two little pictures are supposed to be those alphas, right? So if I'm not mistaken, I think it was exactly like that. So then somehow you have the block splits into two things, which is kind of funny. And this is also like what you see in Cardy's formula, it's something outside of minimal model. So upshot here is that we are outside the minimal model. Yeah. But I haven't, because every minimal model, I think you should do somehow maybe separately, or maybe you have some systematic way. So I haven't, this is the only case I just investigated a little bit. Yeah. But it seems to be there. And I think it's actually one of these other bases I mentioned. So I said there's this basis of conform blocks that we call Z, somehow partition function Z. So there are other bases, and there's one basis that's particularly interesting that I think gives the minimal model blocks. And it's the one who some of them will be killed by this map also. So yeah.
The second theorem, can you give a reference for this?
Which one?
The second theorem.
This one. Ah, yeah. It's in my paper with Kalle. Which year is it? It's in James. I think you'll find it by this thing.
Or if you didn't write the last name, I'm not sure everybody knows.
Ah, yes. Okay. Good. He's gonna be here also, so I think you will know him later. I forget when it was published. And yeah, there's some stuff in my PhD thesis introduction.
Well, what is the statement of the theorem? I mean, of course, I mean, a vector space I can embed into a bigger vector space.
There's actually another paper also. I think we need to combine them. Yeah. So there's a much more structure
That
here.
should be structure, yes,
Right.
because just embedding vector spaces is not.
So they as highest weight vectors.
In the image.
In the image.
the highest weight
Exactly.
vectors. Yeah.
Yes.
Do you think there is temporal algebra action and it's temporal
Yes.
equivariant?
Oh yeah, so then you can do, if you want all that, but that's not probabilistic tool, so I wasn't somehow thinking of talking about that. But this one, of course, you can write as pi module with temporally leap and this quantum group. And maybe you can imagine how temporally leap algebra acts on these things because of the pictures, right?
Yeah.
So if you don't know what temporally leap algebra is, don't worry, it was just to answer, right? But the thing is that this is not the web basis, it's some other basis. So you don't do the usual action. So this is dual to the web basis. Okay. It's all very complicated. I hoped it would have been easy like 15 years ago, but then I realized it's not so easy. So somehow everything is a bit twisted. Yeah. And of course, I didn't tell you what the Q is. So there's 4 pi over kappa times I, so it's on the circle. And that's why kappa going to 0 is a bit weird. Okay, so now there's a lot of stuff in this remark, because I just wanted to make remark to give some pointers. But you tell me if you have some more question, maybe while I can erase that one, right? I think I need a semester to lecture all these things. And happy to explain more privately if whoever wants to hear whatever, please. But yeah, actually maybe one comment. So on those general pictures historically, so we started with the Coulomb gas integrals and this quantum group structure, which is actually quite nice because it tells you somehow which Coulomb gas integral to pick for each kind of connection pattern. But we couldn't prove that those formulas are positive. And we somehow need them to be positive. Maybe one indication is that this is some total mass. Another one is that we cannot do this SLE theory if we don't have positive function. But no one is telling that Coulomb gas integral is positive. So what we did with the easiest piece, we couldn't get completely to the SLE picture because of lack of positivity for arbitrary many points. So for a few points you can check, right? So then that's why what is here was kind of, for me, marvelous, because we could say it's positive and it agrees with the other one. So then we could use both tools. And this happened when I moved to Geneva and started to work with Hao and started to learn probability, which I didn't really know. So it's possible to learn probability if you're not a probabilist. Okay. Great. So then I guess I need to say somehow why these BBC equations hold. We have some time. Okay. Yeah. Let's do that. Yes, indeed. We know the existence of singular vectors from the Feiking books, but we don't know if they are in this theory. And I was trying to think if there's any argument, not probabilistic, but I don't know of any, but maybe someone has some more new work that will help here. So I will have to give the probabilistic thing. So let's see how to do it. So somehow the key is a martingale argument. And if you don't know what martingales are, don't worry. I will relate to that measure, okay? So there's some theorem by Kirsanov. Maybe I shouldn't, I'm not gonna formulate it, so. Which is kind of a counterpart of Radon-Nikodym theorem. If you heard about Radon-Nikodym theorem in the measure theory, right? So this is what I was using here essentially. This is the Radon-Nikodym derivative of the actual measure that I want with respect to the independent measure. So in other words, it gives the interaction. Yeah. So there's in a probability theory, there is a theorem that tells a little bit more about this Radon-Nikodym derivative. Which is that, let me call it Rn derivative, by which I mean this weird thing. I guess it was the independent one. So it's that thing. So it has to come from some martingale. So I call it martingale like that. And so what does this help? It gives us some information. Okay. So if you do probability, very often you use martingale. But what does it concretely mean? So it tells us how the randomness is somehow changed, right? This one. So there's randomness from Brownian motion. And now I do the picture again about the nice curve and some points. And this map. And yeah. So now, if I want to have this multi-curve model, I need to keep track of not only one curve, but also those other mark points. Maybe have some other color. So let's imagine that I'm drawing this first curve. And then these other curves might grow later or whatever, right? So I can do that. It's like I'm exploring from here one of these at the time. And again, I can do this kind of linear theory, which tells me that if I know how the tip goes, I know everything. And also these points are moving. So they're gonna be like GT of x2. This was x2. This was x1, etc. Maybe x1 is 0. So the point I'm trying to make is that if there's no other points, right, then this one was just the Brownian motion, which gives all the randomness. But if there are these other points, I need interaction here, which is what people call a drift. So what does it look like? It's going to be something that you accumulate in time of some stuff. I write maybe in a differential form soon. So the Kirsanov theorem kind of tells us that this quantity gives rise to something here. So it changes the randomness of the Brownian motion to involve this interaction. I know it's extremely imprecise, but I think if you're a probabilist, this is completely clear. And if you're not, I think probably doesn't help to go to the formality too much. So what we get is that this W has to be, let me like write the differential notation because it's easier. Let's see. So it has some kind of function, which is exactly that set, differentiated and added to the thing. And here is dt. So somehow when I look at the little time increment, I have the time evolution of the Brownian motion over here. And then some other time evolution, that's all these points. So these are the points in red. And that's this special one. And what is here? So this one is our partition function. Maybe I could have the alpha label if I wanted. So here's a log. Maybe one way to see it is that this is going to look like exponential of some stuff in this Kirsanov theorem. And it's not unlikely because we see exponential there. And that gives the positivity. So somehow exponential of things, real value things are positive. So that's why log. I don't know if it helps. And so this partial one is the derivative with respect to this variable. It's somehow telling me how much the interaction changes when I evolve here. And the kappa is the strength again, right? So that's a formula we get from this Kirsanov theorem. And I'm hoping it helps to understand the BBC equation because now the function appears here. So that function, so we got rid of all this loop measure that we don't quite understand, right? So I wrote some formula for this function that was coming from the measure theory. But all I want to understand for the BBC equation is how does it evolve when I move these points, right? Because the BBC equation is about those insertions. So now I just investigate that one, okay? And somehow, yeah, evolution here, you can somehow maybe even think about how the BBC equation tells you about evolution of, if you move the insertion a little bit, something like that. So here they are kind of moving, it's some particle system. And now, finally, so how do we get to any BBC? Maybe it's a bit mysterious, but this martingale that we have has a specific form. I think I have to write it. Cannot avoid. I'm sorry. But let me write it. So it's what's a martingale? It's a process in time. And it's built from this interaction. So I can write it as just a z times some prefactor. So let me write here gt of x hat, which is all these other points, because I don't want to all the time write them. Right? It's just that. And then here I need to put something, which is the effect of the change. So here, this is somehow the half plane minus this piece, right? And here's the half plane. So again, there's some evolution of going from the slit half plane back to the half plane. And that gives me these h12 powers here. And in the end of the day, what comes is the derivatives of the conformal map, which now is this one at those points. Goes from 2 to n, because it's the other points, right? Something like that. So I hope it makes some sense. It comes from this black box, but the upshot is that we have some kind of object which is very useful for probabilists. Okay, and on the right hand side, we have this confa block evaluated at this time evolved points. But what does it mean is that I need to do the word identity. Does it make any sense? Yeah.
So am I going to 2n, or is there a difference?
2n, yeah.
Paired x.
Yeah, sorry. There's n curves and 2n points in my picture. Thanks. And somehow the curve didn't matter too much anymore because I was interested in these particles, which are the insertions of this whatever field, right?
But it somehow doesn't see the pairing of the other lines.
So there is the pairing, indeed. And do this. So in the future, this would of course go somewhere. And it turns out that it wants to go to one of these. So this interaction somehow is attractive. It's not clear from here, but you know. So then let's say maybe this wants to go here. And then later these would pair, whatever. So there would be a pairing secretly here. And also there. So if time goes to infinity, I would get wherever this was supposed to go, it will end. And then I could iterate to do the other ones. So let's say it was like that. So of course the iteration I need to do in a separate step.
This is in the z part.
And then the z will have this called alpha, right? Exactly. So this is telling us how this curves eventually pair. Pair the points. Yeah. And of course, if you only have 2 points, it's easy because then there's no pairing, and this is just a 2-point function. So actually, if you do the exercise with the 2-point, you see the 2-point function that I was calling Poisson kernel here. Because in general domain, it doesn't have formula. For more points, you need all this stuff. But it always looks like that you get some kind of time evolution that evolves in a nice way, which is turned martingale, which means that somehow if you explore up to some time, so then the rest is only depending on somehow the shape what happened. So it's almost like it forgets its past, but doesn't completely because, you know, the shape. But on this side is some kind of Markovian process. I don't know if I can explain better without going to the details, but so then the black box that I need to do for you. So from general theory, let's say, martingale theory, something like that. Right. What do we know is that if we differentiate this guy, okay, I do some kind of stochastic differentiation. It's gonna be having some stuff. You can explicitly do it, but of course it has derivatives of this guy, right? And then some stuff from here. And here is still Brownian motion, plus maybe possibly some stuff. So why Brownian motion? Because it was still here, right? It's the only randomness. And there is possibly other stuff when you calculate. So there are two parts. There's the Brownian motion part that we kind of are not very concerned about because we like it. It gives us the randomness. And then there's this interaction part, which I call like dt, infinitesimally in time. People call it finite variation part or whatever. So if you calculate for this m, so it's a random process similarly as this one. It's just a bit more complicated. So you can do some computation to see the two parts. And the point is that when we know it's a martingale, then this part has to vanish. So martingale is something that's almost like Brownian motion up to some kind of change. So maybe that's one idea to understand. So let me write here. So he points then is that this is not there. Martingale doesn't have a drift. Drift is this dt part. Let me call it drift. So it behaves like Brownian motion with some kind of change. And now if you look in the end of the day, what this has eaten, so when you do the computation, this is explicit. Maybe I write it in the next board, but it's essentially the BBC equation. So that's somehow the root to prove it, but I need to give you a little bit more, I think, so that you can get anything out of it. Yeah.
3 minutes.
3 minutes. Okay. Then I cannot give you much more. So there is this stochastic calculus that people do. So you know your usual calculus, you have functions, you differentiate them and you integrate them, right? So if you have random processes like that, you can do stochastic calculus. But if you try to differentiate somehow Brownian motion, it's not differentiable. So that results in some kind of higher order correction terms that are in these ... things. And that's somehow what gives rise to this kind of drift thingy. So if you do it from stochastic calculus or Ito calculus, you can calculate this MT derivative. And okay, so we didn't care about the Brownian motion. And here you get something very big. Maybe I cannot write it if I had 3 minutes. But I can write maybe something. It's partial 1 squared c plus sum over the other ones. Partial c. Yeah, plus a constant term. And here is 2 h1 2. Okay. I think you start seeing something now. Oh, xi minus xj, maybe 1 minus j. Okay, so this hopefully looks a bit like BBC equation in some form. So what is happening here is like second order derivative, which is the highest one. And this comes from somehow when you differentiate Brownian motion, something like that. It's called Ito's formula. And then there's first order derivative and constant, and it's all homogeneous. So what you can get from here, so I will stop, I just make upshot.
This is all with x1. The first term is just x1, and so you're just looking at how the gamma curve interacts with the other things. The other things are never interacting.
So they are somehow moving, but then of course I could pick any other curve than the first one. I just decide to, it's the easiest to write for me,
Right.
because everything is completely symmetric. So I can decide which one, and for each one I get this. So indeed, so this one, this is a BBC equation. 4 is phi 1, 2 at x1. And I think it's, so here is the conval weights of the other ones, right? How to write weights of phi x2 dot dot dot. And we happen to know they were 1, 2. In principle, you could have other things there, right? But in my example, it's just everyone has the same weight. So you do this for the others, you get the BBC for each of them. And only level 2. So upshot is that level 2 BBC, you really get from probability. But then you can do fusion to get higher level. So you actually get all somehow catch table, but in the first row here. So you get like H1, 3, 4, etc. And what does it look like? Just make one picture. So this is H1, I don't know, S. If I have is -1 curves here. So the recipe somehow is that by fusion, you can take these curves to start from same point and you get this higher patch things. And, I think I will stop, but I'm taking questions if there's time. Thanks.
Thank you. Eveliina, for a very nice talk. So are there still some other questions?
Well, can you comment about the Bauer-Bernard theory which they use?
Yes. Right. So I comment about. So they already had this martingale idea. So I don't know if it was actually the first instance. Yeah, because they got really interested. Yeah, it's Bauer and Bernard. They got really interested in SLE when it was introduced. And I think they used this Kirsanov idea to actually see that indeed this thing should be true. So here what you need to worry about is that if you can differentiate, and of course then needed some mathematical work to do more precisely, but they had this idea that any kind of martingale which has this property will actually have to do with Virasoro general field. Yeah.
Now, what would you have to do to go to H22?
Great question. So you should combine with the dual SLE and then fuse. But at the moment, we don't know how to do it. Maybe someone knows, Baojun?
I want to ask some question.
Okay, I was hoping maybe you can do it. Yeah, please.
So if we have more than 2 SLE start from the same initial point, is it still possible to use this kind of restriction to define this multiple SLE?
Like this one?
Yeah.
Yeah, so you need to do something where you don't allow them to. So let's say it's where they're ending. So you have to do something where, yeah, so I guess short answer is no, but you can take some limiting procedure. Yeah, because this Brownian loop measure blows up.
So I first do this kind of multiple SLE, then do some fusion.
Yeah, or you can, let's say if you want this radial case, you can do, I think you may have seen it. So if you have interior point where they want to grow instead of the boundary point, you somehow, you can do for any time, and then you take some limit, and you can actually prove that it works. But the Brownian loop measure, I don't think anyone investigated completely how there's some divergence that you somehow renormalize to get this. Yeah.
Thank you.
So when you talk about Dotsenko-Fadeev and so on, there's always this free field theory in the picture, right? So you have a much easier free field theory where the correlators are maybe just this first product of xi minus xj to some. Yeah. I mean, there is things like this, right? And I'm wondering whether this is on the stochastical side visible. So for example, there should be some correlation function that come from the free field theory, but there is more. And there should be some part of the fusion rules you see, but there is more. So can you see this on the side?
So if you do this kappa equals 4 case, there it's related to the free field theory. So you can see something where it's really, you have this kind of positive and negative charges, and it's quite, then it's quite simple. It's just product of things. I guess maybe you can do some central charge modification if you want this other free theories. There's work of Makarov and Kang, for example, kind of related to that. So you kind of see it. So here what should actually happen should be this kind of thing with imaginary coupled Liouville potential, something like that. But so that would be maybe a route to construct these things. And I'm looking at all the people doing that stuff. Help me with that. But this is what physicists believe. It's somehow strongly coupled. And it's also non-local, right? Because of this. Those curves somehow, yeah, it's kind of complicated.
Do you have a SLE model for bulk correlators? Can you calculate?
Yeah, so there was one picture here.
Yeah, but I didn't get that.
So it's kind of going slowly in this business because bulk field doesn't have BBC equation. Maybe I should have said what this field is. So here, if I have some number of curves going there, let's say L curves, I will get phi 0, L over 2, which has this catch label, but it's not in the catch table. And you could do some rotation to put the magnetic charge. So there's some stuff like that for the bulk, if you want endpoints in the bulk. But then there are these things that have, you have a point and you want surrounding. SLE loop or CLE loop, and we might hear about this in the program. Not quite sure. I think Johan kind of talked about this a little bit. Shin, if Shin is here, he has some work on the 3-point function in this case that coincides with this imaginary DOCC up to some, yeah. So there are some things one can do. Yeah.
But indeed, it is a mystery how you can define a connectivity probability in the bulk, and then you can send a point on the boundary and it becomes BPZ. So we have not understood how it works.
So we
know now the function in the bulk.
Yeah.
By bootstrap. We know the one on the boundary, but the limit, how you do from one to the other.
Yeah, so we can actually prove in this case, if you take this point, let's say in Z, when it goes to the boundary, it becomes that.
Yes.
And then I was hoping if you have a magnetic charge, which gives a twist, it would give something else. But unfortunately, we give the same thing. So we didn't get, Silvan was asking me if we can produce some things with monodromy on the boundary, and it's not that one. So maybe there's something else. So I don't know the CFT mechanism. This is, I try to ask all the time. So now we can prove probabilistically. So this model we can do, and then we can prove the convergence, yeah. It's not out yet, yeah, but hopefully it's out very soon because I was trying to finish it yesterday, so. But it's hard to read maybe for the except introduction because there's probability arguments, but yeah. So we can do it now, but for me it's mysterious as well. Like you have this one, it becomes the phi 1, sorry, 1 whatever, L minus plus 1.
Yeah, so I think we can have more questions during the coffee break.
Yeah,
so I think we can thank Eveliina for the very nice lectures. 15 minutes. Okay, welcome back. So to this morning session. So we have the first talk on the lecture